Okay, hi. So in this video, we're going to cover two different types of energy transfer, which are known as conduction and convection. And so first of all, let's take a look at what we mean by conduction. Now, conduction is energy transfer. So energy transfer through a material. And it's normally, but not always, and that's why it's in brackets, it's normally going to be through a solid. Most of the time we talk about solids when we're talking about conductors. Now, the reason I've said energy transfer is because you will have heard of electrical conductivity, so wires allow electricity to pass through them, but we also talk about conductors of heat. So the main two types of conduction are heat and electricity. However, in this video, I'm going to focus mainly on conducting heat. Conducting electricity is something for a later topic. And you will have heard of good insulators. We talk about insulators a lot. And that is the opposite to good conductors. So a conductor or a good conductor is the opposite of a good insulator. So conduction, opposite of insulation. Okay, now let's have a look at the difference between a good conductor and a poor conductor of heat. So a good conductor of heat is something like a metal. So metals in general are very good conductors of heat. And on the other side, we're going to have something like, let's just say salt. The reason I've picked these two is because they're both solids at room temperature and they both form crystal structures, but there is a key difference. So in a metal, we will have this arrangement, but the key here, if you think back to chemistry, is that each one of these metal atoms actually becomes a positive ion. And it does that by releasing electrons. And so if I'll do it in green, we have electrons which are free to just move around wherever they want. And there we go, that's probably clearer in red actually. Okay, so these electrons are able to just buzz around, they can diffuse wherever they want throughout the metal structure. The ions, so these positive ions, which used to be atoms, have to stay where they are, but the electrons can go wherever they want. And so if, for example, I added heat to this side, what could happen is an electron gains energy from the thermal energy, which has obviously been provided by heat. That electron can now buzz around and it can do whatever it wants. Other electrons will do the same thing. They'll buzz around and eventually you have these electrons which have a lot of thermal energy. And so with the circle around them here means they've got a lot of thermal energy. And so what's happened there is that the heat has quickly diffused throughout the metal via these electrons. Because the electrons are free and delocalized, it means that they can move. So good conductor, because electrons free to move, and that allows obviously the spread of this heat energy very quickly. But now what if we had a salt? So a salt will have a crystal structure as well. Obviously I'm going to simplify it and say that it's exactly the same. But we don't have any free electrons in a salt. Not at all. What we have is ionic bonding holding these together. And so everything is rigidly stuck in place and we've got no diffusion. So let's say we add heat here. So heat on this side. What will happen is each one of these will heat up. So these are actually ions, but it doesn't matter. In some solids, there'd be atoms. So these will heat up and they start to vibrate. So this is a vibration. Okay? They're vibrating because they have a lot of energy. Now, they vibrate and they'll obviously bump into their next door neighbour. That will then transfer some of the energy to the next door neighbour. And then they will heat up. And then the energy will be transferred to their neighbour because they've vibrated into the next door neighbours again. So we have slow movement here of vibrations throughout the solid. So the vibrations mean slow movement And that's because this guy, if he was vibrating, he cannot vibrate into that guy down there. Whereas this electron, if I had an electron here, he absolutely can diffuse through the metal and not bump into anything else and end up down here. So the heat has been transferred way more quickly. Now, I know this is starting to look like a bit of a mess, so I'm going to just tidy it up. Okay, so you get the idea. We've got slow movement due to no free particles. No particles to freely carry heat. Okay, now importantly, we can test the difference in how good a conductor different materials are. And one way we can do that is we can take rods of different materials. Now let's say, for example, this green one here, that is some sort of plastic. This white one here, that might be some sort of wood, obviously painted. And then this last one is going to be a metal. Now what we've done is we've applied a Bunsen flame, so Bunsen flame, to one end of each rod. Now each rod, importantly, has to have the same diameter. So very important, same diameter. Because if you have something really thin or really thick, then it changes how much they conduct. So same diameter. And the rods are also going to be the same length. And these Bunsens are going to be the same temperature. So there are lots of things we need to keep the same. But what we've got here is we have matchsticks which are stuck on using wax. So this here is wax. Now, we heat one end and we have applied matchsticks all across these rods. After a while, the matchsticks will fall off because the wax will melt. Okay? And now we can see on the metal rod, so here, all of these matchsticks on the floor have already fallen off. And so that's great because it shows that heat has been conducted and it's caused them to fall off. If we have a look on the other end, we look at this plastic rod up here, all of the matchsticks are still in place. And that is because the heat has not been able to be transferred through the plastic. So the plastic is a good insulator, it's not a great conductor, so that means the heat has not moved from this end of the plastic to the other end. Now there are various other experiments as well that we can do. One of them, for example, we can look at the temperature change if we put a heated cup or something like that in a material. So we know that some materials are great insulators, and so we just time how long it takes for the temperature to go down. If it takes a long time, then it means they're a good insulator and a really bad conductor. If it takes a really short time, then the heat has been conducted quickly away from our cup of water or whatever it is, and that would make a good conductor. Okay, so I hope that makes sense. I hope you now get what conduction is in terms of heat. And now we're going to move on to convection. Okay, and so now we're going to quickly run over the idea of convection. Now, convection you will have heard of in the term of a convection current. So convection is another example of energy movement, just like in conduction. Energy movement, and this is via convection currents. So convection currents. Now what's very important is that this occurs in the fluids, and you'll remember from the states of matter video that the fluids, that's bad handwriting, isn't it? The fluids are the states of matter that flow. So the fluids are the liquids and the gases. So a convection current can form in a liquid or in a gas, but you're not going to find it in solids. So heat travelling through metal is not going to cause a convection current. Now, I'm not a big fan, really, of the way that this is taught in the books, because in your textbook, you see various examples of convection currents in real life without really understanding how a convection current works. And then that comes afterwards. So I'm going to go through a convection current first, and then we're going to go through a couple of examples. Okay, so here we can see we have a flame. So we've got a flame here. And all that's doing, obviously, is it's providing heat. So let's just do that in red. That is providing heat to the bottom of this beaker. Now this beaker, as you can see, contains water, and the water at the bottom of the beaker is of course being heated up. Now this is going to set up a convection current. These arrows show the movement of water. So if you can imagine a tiny little molecule of water, let's just draw it as this blob. This of course isn't chemically correct, you've got 3 atoms in water, but just so you can get the picture. Now this molecule of water is being heated, it's getting loads of energy, and that causes it to rise up. And as it rises up, it cools down, and then it starts slowing down a bit. There we go. It starts slowing down a bit, so then it's not got as much energy and it starts to fall again. As it falls, the temperature goes up and it starts buzzing again, and it gets really excited, and then it starts rising up again. Now that's a simplistic view of what's really going on. What's happening is that because down here all the water molecules have got a lot of energy and they're moving fast, it means that they can move further apart, and that means that they are less dense. If they are less dense, the cold water is more dense, and therefore the cold water will sink below the hot water. So if something is not dense, so less dense, rises, more dense, sinks. That's why if we put something like a cannonball in water, it's going to sink to the bottom because it's so dense. Whereas if you put a feather on water, it floats because it's not very dense. Okay, so the more dense cold water falls, and then it gets heated up. And at the same time, the hot water, which was hot water previously, is cooling down. And then it's a role reversal. So then the hot water cools down, and then that will sink, and so on. And that movement of water is known as a convection current. Now this doesn't only happen in water, I said that it happens in fluids, and so this also happens in the air, it can happen in gases and any other liquids. Okay, and so an example of another convection current which is in gases is the idea of a sea breeze. And so here we have a simple diagram showing the sea on this side, so this is the sea, and then of course we've got the land over here. Now what's happening is that, of course, the surface of the water, the sea, is generally colder than it is on the land. There are exceptions in some places, but a lot of the time this is the case. Now what happens then is the air, so here, the air over the sea is going to be cooled down by the surface of the sea. And cool air sinks. So it sinks, and eventually it will move and it will move, and some of it will get to the land. And what's going to happen over the land is that the land is warmer, and so that means that the land is going to warm up the air, and the air is therefore going to rise, and so the air is going to rise up, and that air rising will leave a gap, and that gap causes the cool air from here to be pushed this way. So this blue arrow is showing where the cool air is being pushed. That's because there's an empty hole where the warm air has moved upwards. And then as it gets up here and up here, it will start to cool down. So it will cool down again. And that is because it's further away from the land. And so when it's further away from the land, it's got nothing to heat it up anymore. So it cools down. And because there's a constant movement of this air going up, it's going to move away from the land, like here. And then it's going to sink because now it's cooled down. So it sinks. Is being cooled down even more by the sea, and then we get a cycle. And so this going round, so here we go, this going all the way round is a cycle. We call this a convection current. So the convection current here is the air moving across, being warmed, moving up, then cooling down, sinking, and repeating the process. And this is actually the movement of air, and of course the movement of air equals wind, and that is why we have a breeze on the seaside, where you might not have one on sort of in the centre of the mainland. Okay, so that's a real life example, again, of a convection current in action. So I'm going to wrap up there. I hope that's been helpful and that you now understand the idea of conduction and convection in terms of energy transfer. If you do have any questions, please do email me using the link below, or you can post a comment and I'll be sure to get back to you. But I look forward to seeing you in the next video.